Hello, calculus fans. Let's make a definition to say that a vector function is continuous at a point A, provided the limit as t approaches a of r of t is equal to r of a. So, in view of the definition of a limit of vector functions, we can say that r is continuous at a if and only if the component functions are continuous at a. What I'd like to do is make a connection between continuous vector functions and space curves. Let's suppose that we have f, g, and h. They're continuous, real-valued functions defined on some interval I. And then the set of all points in space where x equals f of t, y equals g of t, z equals h of t, where t varies throughout the interval I. This is called a space curve. You're tracing out a curve in space as you follow along these component functions. Now, we've used this kind of thing before. These are called parametric equations of the curve. We used this in the context of lines. We wrote down parametric equations for lines. And t is called a parameter. All right, now let's think of c as being traced out by a moving particle. And its position at time t will be the point f of t, g of t, h of t. Then the vector function will be the position of the point on the curve. So we can say that any continuous vector function defines a space curve that is traced out by the tip of the vector that changes. Here's a picture to illustrate what we're talking about. So the thing in red is the space curve. The arrow is just cluing us in as to the direction that the space curve is moving. The point P is giving us a point on the curve. The blue vector is pointing to a spot on the curve, and it is the vector whose components are f, g, and h. Okay, that's all for now.